Hello guys, welcome to today's class. In today's class, we'll be discussing the concept of higher derivatives. And in this class, we'll be able to understand what first derivative means, what second derivative means, and the nth derivatives. Now, if you are given a function y equal to f of x, if you have a function defined this way, y as a function of x, and you are asked to differentiate this function, the initial differentiation you'll be making on this is called the first derivative. And you remember, because y is a function of x, we're differentiating y with respect to x. So we'll have dy dx. And on this, we'll have f prime of x. This is called the first derivative made with respect to x. It's called the f prime of x. Now, if you are asked to find the second derivative, it means we'll have to differentiate this the second time. And if we should differentiate this, we'll have the squared y dx squared. This is called the second derivative. And on this, we have f prime prime of x. This is the first derivative. This is the second derivative. Now, this from the second derivative, we call them the higher derivatives. Now, if you can differentiate continuously this way, you can find the third derivative, the fourth derivative, till the nth derivative. Nth derivative simply means to any order, to any power. So, I can have the n y the x n. This is called the nth derivative. So, any derivative greater than 1 is called a higher derivative. So, we can write it this way, fn of x. Now, we will now look at some practical examples where we have proofs involving higher derivatives. Let's look at this practical example. Given that y equal to a sine alpha x plus beta, where a, alpha, and beta are constants, prove that the squared y dx squared plus alpha squared y equal to 0. Now, in this example, we are going to see how we apply second derivative, which is higher derivative, and how we use them in proofs in this form. Now, if you follow through this video to the end and you appreciate the video, you love the video, do wait to like and subscribe to the channel so you get notifications when I upload new videos. Now, let's get into the question. Prove that the squared y, the x squared, plus alpha squared y equal to 0. So we have solution here. The first thing we do is to write the function. Our function is y equal to a sine alpha x plus beta. Remember, while solving this problem, your mind should always go to what you are solving. The main question is prove that this is equal to 0. And if you look at this, we definitely need to find the first derivative, right, before we get the second derivative, because we have a second derivative here. But before you get to the second derivative, you must find the first derivative. And when we get the second derivative, we can now substitute everything into this equation. Okay, now let's say we have y equal to this. The first thing we need to do is to find dy dx. Our dy dx will be, how do we differentiate this? To differentiate this is a constant. Remember, we said that a, alpha, and beta are constant. You keep the constant by the side and then differentiate the function. Now, if I keep a constant and I'm differentiating this, remember the rule of chained functions. How we differentiate chain functions? First, we go into the function. This is a chain function because it's sign of something. So we go to the inner values and then differentiate them. Then we'll go outward, right? So let's differentiate this one inside. To differentiate this, we have alpha x plus beta. First, we start with alpha x. If you differentiate alpha x, you have alpha, right? If you differentiate alpha x, you have alpha. If you differentiate beta, that's 0. So we are done with this inner value here. So we go outward. We now differentiate sine. Anything is cosine of that value. So we have the cosine of alpha x plus beta. And the next part is just to simplify this, and we are done with this derivative. So this gives us alpha a cos alpha x plus beta. Now, I can as well keep this thing as a alpha or alpha a. Anyone is fine. So this is our first derivative. But in the proof, we are required to prove that the squared y, which is the second derivative. So definitely we need to find the second derivative here. So let's go for the second derivative. Our second derivative will be the squared y, the x squared. So we need to differentiate this. Now this is a constant, this is a constant. So we need to keep the constant by the side. I have a video on constant rule, how you differentiate a function having a constant coefficient. Okay, so we keep the constant by the side and then differentiate this. So let's start. For you to differentiate this, like we said, you need to go to the inner function, differentiate alpha x. So let's keep it this way. Differentiate alpha x, you have alpha. Now differentiate b is 0. Now we are done with the inside value. We go to cos. To differentiate cosine, when you differentiate cosine, you have a negative sign of the value inside. So we have a negative sign alpha x plus beta. Okay, so this is our derivative. So we now simplify from this point. So if we simplify here, alpha times alpha is alpha squared, but we have a negative here. In the rule of directed numbers, we always bring out the signs first. So negative comes out first. So you have alpha times alpha, you have alpha squared. A times everything here, you have a sine alpha x plus beta. Okay, so this is our second derivative. We'll be able to get our second derivative here. Now at this point, we can now substitute into this equation. So we now write substituting we are substituting y, the squared y, the x squared, into the equation. Let's rewrite the equation. Look at our equation. We have the squared y, the x squared, plus alpha squared y equal to 0. So we need to substitute the value we have for y. Remember our y is this. We substitute that value into the y here. We also substitute the value of the squared y, the x squared, which is this, into this. And then we simplify. And that, when we simplify, we'll get the solution to this problem. We'll see if it will be equal to 0. We have our y equal to this, our second derivative here equal to this. Now let's substitute into this equation the values for y and the squared y, the x squared. So we'll be having, for the squared y, the x squared, we'll be having negative alpha squared a sine alpha x plus beta. That is for this. Now plus, we have alpha squared, and the value for our y is a sine alpha x plus beta. And let's see if everything will give us 0. Now this will be equal to, we have a negative alpha squared a sine alpha x plus beta and a positive. So this is more like a negative value plus that same value, and that is definitely equal to 0, right? And this is proved here. Let's look at yet another example on proofs involving higher derivatives. Let's look at this second example. Let y equal to exponential ax sine x. Prove that the squared y, the x squared, minus 2a dy dx plus a squared plus 1 into y equal to 0. Now let's see how we can prove this using the idea of higher derivatives. Now we have the function y equal to exponential ax sine x. First, we bring that function out, exponential ax sine x. And then the next thing we do is to look at the equation we want to prove out. We have a first derivative here. We have our y here. We have our first derivative. We have our second derivative. And so definitely we need to find these various derivatives. Okay, so let's get our first derivative from here. Our first derivative will be the y, the x, right? And to differentiate this, we definitely need to apply our product rule, because this is an exponential function, this is a trig function multiplied. And so we need to apply our product rule. And what does product rule say? We have to hold the first term here, the first function, exponential ax, hold the first term, differentiate the second, then plus hold the second, differentiate the first, right? So we hold the first function here, exponential ax. We differentiate sine x. We'll have cos x. Okay. Now plus we now hold sine x, differentiate exponential x. Now the differential of exponential x. First, we have to differentiate this index here. We have to differentiate this. If we differentiate this, we have a. Differential of ax is a. So we have a, and then we differentiate exponential x. This is a chain function too. So we differentiate this function as the index, and then before we differentiate the exponential function. Whenever you differentiate exponential anything, it's still that value. So we have exponential ax. Okay, so we've completed the product rule on this. The next thing is just to simplify this. We'll have exponential ax cos x plus we bring out this term. This is a exponential ax. I would prefer to bring out the constant term and the exponential function out before the trig function. And so we have this. Okay, so we've just gotten the function y, the first derivative, which is this. We also need the second derivative here. So let's go to the second derivative. We need to find the squared y, the x squared. And so we have to differentiate these terms here. So we go using our product rule again, because this is a product function. So we hold the first term, exponential x, differentiate sine x, differentiate cos x rather. We differentiate cos x is a negative sine x. And putting it in bracket because of this negative. So you don't assume it's just a subtraction in between. Okay, so we differentiated this. Now plus, we hold this, differentiate this. So we hold cos x, differentiate exponential ax, which we've done before, and that is a exponential ax. We are done with the product rule on this. And then we'll go to differential of this one. Plus, now there is a constant here. We bring out the constant and then tackle the functions directly. So for product rule here, we hold exponential ax, differentiate sine x, you have cos x, plus hold sine x, differentiate exponential ax, you have a exponential ax. Okay, so the next thing is now to simplify everything there. We have a negative exponential ax sine x plus, I will always prefer to bring the exponential term outside, the constant and the exponential term first before the trig sign, before the trig function. Okay, so we have a exponential ax cos x. Now if I open up this bracket, I will have a exponential ax cos x plus, if I multiply this to this, I will have a squared exponential ax sine x. Okay, let's see if some terms can add up from here. Okay, so we have this and this are quite the same, so they can add. So we'll have minus exponential ax sine x. This plus this will give us 2a exponential ax cos x plus a squared exponential ax sine x. This and this can't add, so we keep it this way. So we've been able to get our dy dx and our d squared y dx squared, which is our second derivative. And then the next big task is to substitute into this equation and then simplify. Okay, let's get into action and substitute into this equation and see if we will have 0 at the end of the day. So we have our y equal to this. We have our dy dx. We have our d squared y dx squared as this. And then this is the equation we want to substitute these values into. Now let's get into the substitution. First we have to substitute for the squared y dx squared. And so we have this. So this gives us a negative exponential ax. We have sine x plus 2a exponential ax cos x plus a squared exponential ax sine x. We've substituted for this. Now the next thing is substitute for dy dx. So we have a negative 2a. We are done with this. We move into this. So we have a negative 2a. Then our dy dx is all of this. So we put it in a bracket. We have dy dx exponential ax cos x plus a exponential ax sine x. We've substituted for this. Now the next thing is to continue with this term. We have a plus. This is a squared. Okay, we can actually expand this here. We have a squared y plus this. So, but let's just go with this. We have a squared plus 1. For y, let's just write out the value for y. We have exponential ax sine x. Okay, we can go with this. Now, let's see if everything here will be equal to 0. When we simplify all of this, let's see if this will be equal to 0. So this will be equal to, let's simplify further. This is minus exponential ax sine x plus 2a exponential ax cos x plus a squared exponential ax sine x. Now let's simplify this. It's a long walk, but we will pull it through. So this is minus 2a exponential ax cos x. This also multiply through all of this. So this goes into this. We have a negative 2a squared exponential ax sine x. Okay. Now we also have this term here. This will be a plus. This into this is a squared exponential ax sine x. Right? And then this goes into this. We'll have exponential ax sine x. Let's see what we can make out of this. Okay, so we have, let's look at some terms that can possibly cancel out if we have any. Okay, or some terms that can possibly add up. Okay, so let's look at it carefully. We are seeing this term here, negative exponential ax sine x, and we have a positive exponential ax sine x. So we can rule this off. Okay, let's see more terms that can cancel out. Look at this. We have 2a exponential ax cos x minus 2a exponential ax cos x. So this can also cancel out. Okay, so we are left with this term, this term, this term, and they look quite alike, but let's bring it out. This will give us, let's bring out the term remaining. This is a squared exponential ax sine x minus 2a squared exponential ax sine x plus a squared exponential ax sine x. And we can now see that this to this is a negative a squared exponential ax sine x plus this gives us 0 definitely, and this is proved. All right, so with this example, we've considered the first example and we've considered this second example. You see the concept of higher derivative, that whenever you are given a function y equal to any function of x, you are given a particular higher derivative to differentiate. What you just need to do is to note the order of the derivative. You differentiate the first time, differentiate the second time to that particular order of derivative, and substitute into the particular equation you are required to prove. And then ensure that by simplification, the left-hand side is definitely equal to the right-hand side. And that's how we prove for higher derivatives.